One second, I'm just. Five, 0, 8, 3. Yeah. Oh, yeah, yeah. Somebody brought up aluminum. So I'm just, yeah. Okay, so today's Saturday morning, right? We'll take it a little bit easy. So what I'm going to do is to fill up some of the gaps. You know, we were talking yesterday, day before, and there were some things that we just kind of left in the middle because we had too much discussion or something came up. So what I thought is I will kind of fill up some of those gaps that came to my mind. Where is our, okay. I don't see him yet. Okay, well, maybe, okay, let's see. Okay, that doesn't matter. I mean, we got, oh, Shinde is not there. Should I bring this up afterwards? Okay. Maybe I'll bring this up after they come. Okay. In the meantime, what I will do is okay. Aluminum magnesium alloy. So you just brought up the thought in my head, you know. So recently, the 5000 series okay. 5083 stress corrosion cracking behavior. Because what happened was recently there is a push to use the aluminum magnesium alloys for ships. Okay? But aluminum magnesium alloys, if you make a ship deck or anything, you know, a ship deck, for instance, out of 5000 series alloys, they can get very hot. The ship deck, you know, especially in the middle of the ocean, you know, the ship deck alloy can get very hot and precipitation could progress, right? And so there have been a lot of studies recently, and this is one of the guys, Tarun. This was what year was this? Let's see. Just, you know, I just came to 2011. This study was done by these guys. I'm going to quickly show you some of the things that may be of interest to you. I don't remember everything, the paper. When you talk to me, I thought I should show this. So here is the, let's not worry about this so much. So here is the as received material. Okay? Just as received. Here is the one that is sensitized. So anytime you expose a material like this at a certain temperature, I think this was 175 degrees C, if I remember right. It's been about 8 months or so since I've looked at it. Yeah, 175 Celsius. It was exposed. So like I said, when you expose this material to this high temperature, the grain boundaries, the precipitates start to fill up the grain boundaries. Okay? So you can see that the crack length is increasing as a function of elapsed time. See how long the crack length is. In the as received material, that means the material that was not exposed to temperature. The crack length is about 2.5. And when you do I don't know what kind of experiments these are, but doesn't matter. But as soon as you have the grain boundary precipitates, because of the sensitization, because of the exposure to temperature, the crack length really goes up. So it could be just a specimen with a small crack, could be a dead load type of an experiment, you know. Huh? Fan is too loud. What is that? Yeah, because of the grain boundaries, there are a lot of grain boundaries in the material which are causing a reduction in the ductility. Okay? So the resistance to crack growth has gone down because the grain boundary precipitates are forming here at 175 degrees Celsius. So if you take a aluminum magnesium sample, okay, and if you did a crack growth test, just a simple crack growth test, you put it in the machine, put a dead load, and monitor the crack length. Nothing happens in the as received material, okay? The blue ones. But if I now take the aluminum magnesium, put it in the oven at 175 degrees Celsius for 240 hours. For 240 hours, and take that specimen and put it in the machine, the crack length starts to rise because there are a lot more grain boundaries, precipitates. Do you see what I'm saying? So this is as received, the blue dots. Nothing along the grain boundary, clean grain boundaries. This is 175 degrees Celsius, 240 hours. I'm just putting one grain here, just to show what's going on. Okay, you still have some precipitates, but now you also have these precipitates. These precipitates, yeah, they'll be permanent. Even if the temperature comes down, they will be there. They will be down there. Yeah. Well, I have to be careful when I say the word permanent, because if I put it in the oven at a higher temperature than 175 degrees Celsius, they will dissolve again into the solid solution. So it's like this. So aluminum magnesium solid solution. I take this alloy, 175 degrees Celsius, 240 hours. I get the grain boundary AL3, Mg2 precipitates at the grain boundaries. That is the chemical reaction that is taking place. Okay? But if I go to 400 degrees C, they may all go back in again because the temperature is too high for the solubility. Okay? But if I just cool it to room temperature, they will still stay there. Okay? And if I leave it at 175 degrees for 1,000 hours, they'll get bigger and bigger. These will get bigger and bigger. Okay? So, right.
They are not hit.
No. This one is different because one of our students or one of our lecturers is thinking of working on 5083 alloy. So we had a discussion outside. So I thought I should show him a paper that will be useful for him. Okay? So what I'm saying is that 5000 series aluminum alloy has got a very low density, low weight. So people in the ship business, the Navy, were thinking of using this material for ships. And then the question came up, if in the middle of the ocean, where the temperature is very high, it is exposed to high temperature for a long time in the sea, what will happen to this material? The conclusion was these grain boundary precipitates will form. Okay? But maybe the ship will never go to 175 degrees C. Maybe it will go to 110 C. Well, even 100 degrees C is boiling water, right? Yeah. So only thing is the kinetics will go down. This guy, Tarun, he got a little extra carried away. He put very high temperature, okay? Because he wanted to get experiments done within a reasonable time. If somebody is doing a thesis on this, you can't wait till 5 years for the precipitates to form, right? Because if the ship goes only to 90 degrees, if this material is only exposed to 90 degrees or 80 degrees Celsius, the kinetics, the rate at which the precipitates will become bigger will slow down, right? Because the temperature is slowed down, it's gone down, right? But there is a study here. There are other studies too. I'm just picking out the paper that first came on my computer. Okay? Yeah. You may have to speak up loud a little bit. Sorry. These fans are loud. Yeah. Mm-hmm. Right. Absolutely. Very low melting point. This is going to happen. Yes. Mm-hmm. Mm-hmm.
Again, it gets melted. Again, how to, by the time temperature cooling down.
Right.
Close to it.
There. Yeah.
What happens? Again, after solving orders of this
Yeah.
also get close to it.
Yeah.
Right?
Yeah. That's not going to do anything. Yeah. I can tell you right now. I'll tell you right now. Okay. I'll tell you right now what's going to happen. Here is our eraser. They're both on this side. I'll go here because you can see, but they cannot see. Okay, so this is the experiment that I will tell you to do. So when I come back next time, I'll see your results. So here is a aluminum plate. But before I do anything, I will take 2 plates of 5083. You got to do systematically, otherwise you will be confused as to what the results are. Now I will do my friction stir welding. Okay? So there is my weld nugget. Agree with this terminology? Weld zone, weld nugget. And there is my heat affected zone. And there is my, of course, I'm not drawing everything properly, but there is my base material. Of course, you can draw, if you want to draw like this, you can. It doesn't matter for our discussion. Okay? For our discussion, it doesn't matter. So when you are doing this, what I would do, I would put a thermocouple. This is not necessary to put a thermocouple here. I would not be, that temperature would be high. But if you put a thermocouple here, for instance, okay, a thermocouple on this side, and see what temperature it goes up to be. It will be nice to know what your temperatures are. Then you can forecast whether you're going to see whatever those precipitates are. I'm sure this Al3Mg2 has got a precursor. Okay? So after you do all this, then you take a section, cut it perpendicular to the friction stress W, FSW axis, okay? Whatever it is, 300 revolutions per minute, or whatever the best, I don't know, whatever is the best, 5 inches per minute translation speed, right? You make a section of that, then I'm going to have a section like this with the weld zone or the weld nugget, WN, my heat affected zone. And there is a thermomechanically affected zone also, right? There's also a TMAZ. Thermomechanically affected zone, I forgot about that, right? So you got weld nugget, thermomechanically affected zone, heat affected zone. And I will document all the precipitates. What are the precipitates here? You probably have a dynamically recrystallized microstructure here. With no precipitates. I got a paper on this one, okay? Dynamically recrystallized zone, dynamic recrystallization, okay? So here there will not be any precipitates in the weld zone. Weld zone will not have any precipitates, okay? After friction stir welding. And then you want to see where are the precipitates here? Are they along the grain boundaries? Are they, Then so this is as friction stir welded. As friction stir welded. So number 2, give the heat treatment. Actually, before you give the heat treatment, I don't think you have a residual stress measurement. Then you can choose the heat treatment so that you can relieve the residual stresses, but at the same time, they will be forming grain boundary precipitates in this heat treatment. Look at the when I say look at the grain boundaries, I mean image the grain boundaries. And then you can throw it in the salt bath, whatever you want to do afterwards. But that's the main thing. That's the main part of the whole problem, right? So, yeah. Right, right. Okay, so the dust is all very involved, atom probe and all that stuff. Okay, that's not important. So I wanted to show you this paper. There is another paper here also. I just picked it up. Measuring sensitization. So as a matter of fact, you don't even have to do all this if you don't want to. I mean, you can do it afterwards, but you can do this. Measure sensitization to forget about that will be difficult to do. Just use resistivity measurements. Don't worry about nonlinear acoustics and attenuation. I can tell you what it is if you want me to, but not here. It will take up all day. But I will do resistivity measurements. That will tell you. Just measure current and voltage. I mean, measure current as a function of voltage, but it has to be very, very sensitive. See. Okay. I'm trying to see if there's a figure here that will help you. Okay, that's good enough. So then if you're interested in corrosion, you can take that one sample, small samples. You can cut a lot of samples actually, and you can put it in a salt, take it home, mix some salt in water and throw it there. And just look at it every day, how it looks. Take pictures of it, You can do that. So you were saying something, Chandraji?
What you have said about the
putting
a salt at
yeah. Right. Yeah.
Everywhere 5 series alloys.
Yeah.
Bulk of them is 5052.
Yeah. This is a newer alloy, 5083. Yeah, new alloy. Yeah.
Application is
Yeah.
Lot of 50.
Yeah. Good point. What will be the effect of the precipitates at the grain boundaries? Yeah, that's what we talked about, right? The crack growth, the cracking length increases. Yeah. So 175 degrees centigrade as a function of time. Yeah.
After the some time, precipitation is growing.
Oh, you're asking that question?
Yes.
Okay. I see. Yeah. Okay. So SCP. There are no precipitates at 400 degrees C. Okay? Oh, you wanted the other way around. Okay. Sorry. 175 degrees C, you will nucleate. Okay. So basically, I think this is what you're asking. Size of the precipitate, size and number, I don't know which one will change. Size and number of the precipitates, volume fraction, area fraction. At grain boundaries as a function of time. And I'm heat treating this at 175 degrees Celsius. Like Sir said, this is not actually age hardenable alloy, it's a work hardening alloy. Okay? But this can happen. This happens. That's what we saw. So at time 0, there are no precipitates. Nothing. Then slowly the precipitates, I'm doing it 150, maybe 10 hours. I don't know which way the curve will go. That's what will happen. Okay? Yeah, yeah. Either they may grow or the number can increase, right? So the magnesium from the, there's my grain, these are my grain boundaries. My grain has got aluminum magnesium, okay? But at this temperature, my magnesium is diffusing to the grain boundaries. And it's forming Al3 Mg2. So the magnesium is coming out of the solution. It's diffusing much faster than aluminum. And it's forming Al3 Mg2 precipitates. So anytime, well, I don't want to make a general statement, but in this case, they are deleterious to the material. They're bad for the material. So we showed, right, crack length. Yeah. We showed that the crack length goes up. Yeah. So we showed the graph, right? We just saw the graph. Yeah, that is Al3Mg2. That's intermetallic, yeah. Oh, yeah, yeah, absolutely. Absolutely, it has to. Well, yesterday somebody was talking about underwater friction stir welding. There he is. There is the Guruji of underwater. You can talk to him more. That way, it won't get hot, right? Guarantee? No, I mean, you have to extract the heat somehow from the weld. Yeah. See, that's why it's very important. We can discover all kinds of alloys, but if you cannot manufacture something, what's the point? Right? Agree? That's what we have to do. Manufacturing, friction stir welding, joining, screws, crack growth rates, all these are more important things. But we do the easy things, tensile test, hardness test, all these things. But those are practical things. Those are important things. How do you do friction stir welding underwater so that you can get that answer from him?
For so long.
That leads me to the retrogression re-aging. Let me go there. I have it here for today, so we'll go backwards. So this is completely different from 5,000 material. This is 7,000 alloy, 7,000 series, okay? Which is a little bit different. This is a precipitation hardened alloy. This is a precipitation hardened alloy. I'm going to put this in the precipitation hardened. So this alloy becomes harder, becomes stronger because of precipitates. That's how you do this, okay? Right. So this also goes back to the question that you were you were asking, right? So here is my supersaturated solid solution. That means all the elements, aluminum, magnesium, zinc, copper, those are the main elements. Here, I got everything backwards. Aluminum, zinc, 5.8. Of course, it won't be exactly the same, but a little different. 2.28% magnesium, copper. As long as you remember it's aluminum, zinc, magnesium, copper alloy. That's enough. Okay? There is zirconium, which is a grain refining agent. It's a grain refiner. It controls the grain size in aluminum alloys. Silicon and iron are junk, inclusions. Okay? So that's the game. That's it. You know everything about aluminum alloys if you know that. Okay. So when you have the supersaturated solid solution, so all those elements that I've shown you are in the solid solution. Not all of them, not iron, not silicon, but magnesium, copper, Anyways, those are all in solid solution. And then when you put a little temperature to it, the first thing is, eta prime. That should be eta. Eta prime causes the peak hardening. So, I'm losing my mind. Oh, there it is. So we are doing super saturated solid solution. Let us say we heat treat this at 120 degrees Celsius, okay, for various lengths of time. Just like we did before, hardness versus time. Or this could be yield stress, or anything, whatever you like. Okay, that's the curve, right? Underaged, peak aged, overaged. Yeah. So here, just before here, the GP zones come out. GP1 and GP2. These are Guinea-Preston zones. They're really not precipitates, but they're a collection of atoms. Maybe 15 atoms, 20 atoms collection, okay? They're forming the nucleus for the precipitate next. Are considered to be precursors to the eta prime phase. Okay, this is all fine. Okay. Size and volume fraction changes, fine. That's all fine. This is the eta prime. Maybe I should make that change right now so that, or I can make it later also, but let me write it down. ZN2, right? Or since I'm not sure, so whenever you're not sure, just put X and Y. Variable. Because you don't know exactly what it is. You need the stoichiometry. Okay, mg, x, z, and y. It could be mg3, z, and 2, or whatever it is. But that's the whole thing, right? And the only thing is, this is important, they're hexagonal plate-like structure and forming on the 1-1-1 plane, because that happens to be the slip plane for aluminum. Okay? So they're sitting on this slip plane. Remember always, 111 is the slip plane for aluminum alloys. All aluminum alloys. Aluminum alloys, 111 is the slip plane. 110 is the direction, slip direction. All FCC materials. Okay. So it so happens, aluminum alloys or that 7000 series, let's stay with that, 7075 or 7050 or something else. Highest yield stress at peak aged. Right? Corrosion, stress corrosion cracking, not the best. Let's call this as T6. In T6 condition, this is my T6. Peak aged is my T6 condition. Okay. My yield stress is very good. Highest. Great. My hardness is high. My yield stress is high. Okay. But my corrosion is not good. My stress corrosion cracking is not good. Let's go here. Okay. Overaged. In the overaged condition. Oh, I'm writing too small. Overage condition, yield stress is lower. Huh? But my stress corrosion cracking is high. I'm going to show you later on. Okay? So here my yield stress is high, stress corrosion cracking is low. Here, my yield stress is low, but my stress corrosion cracking is high. Right? But I like to use, as an aircraft guy, I like this. A lot of my products, I want these. But the stress corrosion cracking is bothering me, you know? So what I do, either repair or I go for replace. Because in a cargo plane, there are big longerons. Big longerons, you know, this is the floor of the airplane. Okay? Floor of the airplane. And there is my fuselage, top of the fuselage. There's a big thing that longeron. It goes from the bottom at a slope and it holds everything. Okay? It's like a stiffener, essentially. Okay? Big longeron. It's very big. I mean, I don't know. Those guys probably know better. It's pretty high. I think maybe 3 or 4 floors high, depending on which cargo plane you're talking about. It is in this condition. I will give you the reference. Maybe you can look it up. C141 longeron. Maybe put something like corrosion studies or something. Google, you'll find some paper you'll find at least, I'm sure. Okay? So this problem was there before, for a long time. So okay. Can I huh? Which region is grain bound, GB2? Oh, GB zones, yeah, below that underaged. Yeah, same. They're all here. Yeah. So, yeah, okay. So, I would say right about there, GP1, right about there, GP2, right about there, MgP Al2, which is coherent precipitates. Okay? Same precipitate, semi-coherent. Same precipitates, incoherent. So GP1, GP2, magnesium aluminum phase, which is coherent. That means the atoms are matching up, okay, with the matrix, okay. Something, okay. So if this is my precipitate, this is my precipitate. This whole thing is aluminum. That whole thing is aluminum, and we call that as alpha phase. Okay? That's the nomenclature. We call that as alpha phase, the aluminum, the background aluminum, this floor, okay? And on top of that, we have the phases. These phases, we can call it as beta, okay? So GP1 and GP2, we don't give it any names because they're very early stages, okay? You need a very high resolution microscope to look at them. But the first ones we start to see, the first phase we start to see, we will call that as beta. But just imagine there is another phase that comes after this. Something else comes after this. It doesn't happen in this alloy, but if there is something else that comes, we will call that as gamma. So alpha, beta, gamma, we keep going and going. But alpha always refers to your parent material, right? Okay, thank you for asking. So there's a guy in Israel, Sina, okay? I'm going to erase this. Yeah, okay. I'm going to erase this because I need more room. So people were working as to what is that we can do so that I can have the yield stress of T6. I can also have the stress corrosion cracking resistance of T7. How can I combine these two, and make one heat treatment? That heat treatment we call retrogression and re-aging treatment. Okay? That's what we call as RRA in the aluminum literature. So this is around, I don't know, Sina, maybe 70, something, 75, 78. Oh, this is a much later paper. This is 1998. Let's look at the original paper if you want to read it. Patent. Here, B. Sina. His patent is 1974. US patent, Sina, C-I-N-A. So if you read that patent, you will get a better explanation than I can give you on the retrogression re-aging, because he's the guy who came up with it. Okay, so RRA is a multi-stage heat treatment. It's not actually multi, it's two-stage heat treatment. Okay? Well, maybe three. Okay, we'll see. So that we trade off between T6 and T7. That's what I was talking about there. How can we get yield stress, which is very good at T6, and how can I have the corrosion resistance at T7? I want to have both of them. I want to eat the cake and also on top of the icing, both. Cake and icing, right? Yeah. So the RRA consists of double aging, two aging treatment. Okay. So what do I do? Actually I got a figure for that. I made a figure for you. Just for you, right? Here. So the commercial 7050 aluminum alloy. So I go through all this. So here, I'm here right now, which is solution heat treatment, SHT. So today we're not going to break till I finish these slides. No coffee and no tea. Maybe I want cookies though. Okay, so no solution heat. Solution heat treatment, we quench. Okay, we quench it in ice water, ethylene glycol, whatever. And then we go from here to peakage. So we heat treat the material, we quench it, we go for the peakaged. Okay, I showed you that curve, right? So you know how long you should keep it in the furnace at that temperature. Okay? What is that? Oh, yeah, okay. Air is okay, air is okay. Air is okay. It's been so long, I'm trying to think, yeah. Huh? Oh, for quenching. For quenching, yeah. Oh, you're asking for quenching. Oh, I'm sorry, I thought for heat treating. Yeah. For quenching, you want, yeah. Very agitated water if you have a big piece, because your center will not cool fast as the surface, especially if it's this big, right? But if it's this big, no problem. But if it's this big, yeah. The surface will cool faster and in the middle will not. Actually, there was a problem one time, I remember, back in the late 80s. Soft zones in aluminum alloys. That's what we called it as, soft zones in aluminum alloys, because they were not quenching it right. The middle portion was soft. The upper portion, bottom portion were hard. You learn by mistakes. So mistake is not a bad thing to do. Without a mistake, you will never grow, right? How many times did you fall when you were young? Okay, right? So in this case, actually, yeah, you already have it here. 478 degrees, that's the solution heat treatment here. Okay? Solution heat treatment for 2 hours. Okay? And then you water quench, just like we said, water quench. Then you go for 120 degrees C for 24 hours. So that's your peakaged, water quench. Okay? And this is so that gives you peak aging. That's your peakage treatment. Your overaging treatment is same like that, but 160 degrees for 24 hours, water quench. So if you want to produce a peakage and overaged material, you just follow these two, right? Now in retrogression and reaging, we do solution heat treatment, and then we do this peakage treatment, okay? And then we go for this treatment, 200 degrees C for 30 minutes, and then we do another heat treatment, 120 degrees Celsius for 24 hours. So this is your annealing step in between. So it's not 478, it's 200 degrees C for 30 minutes. So that's your intermediate step, which is going to give you that overaged condition. And then you go back, this is a peakaged, annealing step, okay? And then you put the peakaged again. So dual treatment. So of course he played with this number of times, get it right. So for the 7050 alloy, 70-50 alloy, this is the formula, the secret sauce. But if you have 70-75, then you do something different. A little bit changes. Yes, sir. Water quenching? Not really, no. No. You can air cool it also, but not furnace cooling. You can take the sample out and put it in the air. Okay? If you quench it, you're freezing everything, basically, which is okay. You won't form martensite if that's what you're thinking. Yeah, after aging, water quenching is fine. Water quenching is fine. Right. Yeah, water quenching is okay. Air cooling is also okay. But this is not a big temperature, 120. But if it's titanium alloys, and you air cool it, you'll get completely different from furnace cooling and from water quenching. So in water quenching in titanium alloys, you'll get titanium martensite. Okay? And furnace cooling, you'll get very coarse precipitates. Air cooling, you'll get finer precipitates, naturally, because you're faster cooling, right? You don't have to do every time, but yes, for commercial applications, if you want both a high peak strength, because it costs money. Remember, when you go to the industry, it's a game you're paying constantly, right? A lot of money is going to cost you. If you want to do a component, means laboratory coupons are okay. But if you're talking about a component in an industry, it's going to cost you money. So you really have to decide if you want that RRA, or can you just live with the peak age or overage. Yeah, for most of them, for 70-75, definitely. Small differences between, yeah. Yeah, but 70-75, definitely it has. Yeah, because that is the one that's used all the time in the aircraft for high strength, but people sometimes want some corrosion resistance. Then they use that C141. Did anybody check and see if they can pick it up here? This, in the Google C141 Longeron, Longeron, corrosion. So for something like that, this is a big beam. It's 3 or 4 floors high. I don't know, some of these cargo planes are very big. So if you have to heat treat the whole part, it's going to take a long time. I think they have been doing it with tape, heating tape, because you can't have a furnace that big. And this is not a very high temperature. That's not a very high temperature. You can get it with the heating tape. So if you can put the heating tape, the whole Longeron can get to that temperature. Yeah, commercial industry things is different ballgame. You had a question, right? I know. Did you raise your hand? What was that question? I'm sorry, I couldn't get to you. Yeah. How to put the thermocouples? Oh, Pankaj here. Who's put the thermocouples on the friction stir? Mahesh? You put thermocouples on the friction stir welded? Amit? Amit did. So you basically drill a very thin hole and put your thermocouple there. But you have to have a very good contact. Talk to Amit, the guy in the green shirt, the smart guy. Yeah. Amit will tell you, right, Amit? Yeah, help him out. Yeah, he'll help you. No, that's the only way you can learn, because he has already done it. There is no point in you going and trying everything and spending another month. He's going to tell you quickly what to do. So you just have to be nice to him. Take him out for a lunch or something. Okay, so that's that, right? So here is a, so again, after you do the retrogression and re-aging, you don't have to do a whole bunch of tests. So here is the work done by somebody. Usually I'll put a reference here, but I can tell you what it is. So here, look at it. So, so this is the black is the peak aged. So this is the stress. Strength versus strain. Stress strain curves in air and in sodium chloride solution. Let's look at air. This is after you do the retrogression reagent, okay? Yeah. There is your peak aged. There is your retrogression reaging. There is your overaged. Right in between, just about, and you got the same strength as T6. Okay? You got the same strength, right? The yield stress is right about there for the black line, which is peak aged. And overaged is here. So you have improved the stress, you have improved the strength by almost 75 megapascals. This is about 500. This is about 575. You have almost improved 75 megapascals. That's pretty big. 75 divided by 500, right? Or about 6%. Huh? Yeah, and then okay, let's look at the strain in sodium chloride. That's a better indication because that's corrosion. This is corrosion, right? Sodium chloride solution. The overaged, yeah. Peak aged fails there. Yeah, the peak aged is failing at this strain, right? The overaging is failing at this strain. But look at retrogression reaging. Wow, there. Beautiful. So your experiment is good, right? I mean, it's good. You have produced, by using retrogression reaging, at least on the lab coupons, a strength as good as T6 and as good as T7 when it comes to corrosion. Just by using a double age treatment where you left the matrix precipitates as they are so you can get the strength, okay? And you refine the grain boundary precipitates by the retrogression reaging. And how many of your corrosion people? Yeah, okay. So this is a polarization experiment, right? This is, you can quickly check this one. You know, also you don't have to do a test. You don't have to do a test for 30 days, 40 days. You don't have to. You can just take a potentiostat and do this polarization experiment. Okay, look at these lines. I'm going to show you. Okay. Let's take one first. Peak age, right? Let's take the peak age, the black line. So it goes, doesn't matter that way or this way. Here comes this way, okay? Black line, or this way and then this way. Yeah, this current, oh, 1 second, is it backwards? Okay. Yeah, okay, yeah. Hold on. Peak age, overage, yeah. So look at the top ones first. So look at the current density first. Let's look at the current density. Higher the current density, more the corrosion. Always, always, right? Corrosion is proportional to current, always. I mean, you can put current density if you want. Actually, yeah, current density would be, yeah, current density would be okay. But if you're comparing, then you want current density, okay? So higher the current, more the corrosion. So here, the scale is, so the higher current is this way, to the right. Lower current is to the left. Huh? So this is the worst of all these three. The green is the worst. Okay, actually that's showing overage. Okay, I don't know why. This is peak aged, a little bit better. Look at the retrogression reaging. It's probably going somewhere still. So it's getting lower and lower current density. That means less corrosion. Okay. That's a little different for me. Yeah. So if you have a bad alloy that's corroding, it will have a high corrosion, 10 to the minus 5. If it's getting better in corrosion, it may be like 10 to the minus 8 or something. 3 orders of lower magnitude current density. Okay? So lower current density, higher, better the corrosion. I'm not too happy with this, If I'm the reviewer for this paper, I will say, get your measurements again. It's not completely, right? No, I'm serious. It's not completely. Okay, I'm going backwards here also. Let's look at Rick Ricker's. Okay, then we'll come to that. This guy's a good guy, Rick Ricker. Very good in corrosion. So this has got nothing to do with retrogression reaging. Okay. So 5,000 series and 7,000 series. Doesn't matter. Let's take one alloy and understand what it is, right? So here is my yield stress curve as a function of chloride ion activity. Okay. So you make up a solution with different chloride ion concentration. So you can put different amounts of salt, maybe 1 spoon, 2 spoons. Of course, you got to, if you want to get moles per liter, you probably want to be more accurate, right? But yeah, that's exactly what I'm talking about. I don't know how much half a spoon means in terms of chloride, but that's what we're talking about, right? My friends may think I'm crazy on this camera. Okay. So as the chloride ion concentration gets higher, obviously aluminum alloys do not like chloride ions. It's negative, very bad, right? They don't like it. So the yield stress goes down, the ultimate tensile stress. Okay, but in air, there is my yield stress in air. No problem. Everything is flat line. In air, ultimate tensile stress is flat line. For 70, 75, flat line, yield strength, flat line. But as soon as you have the chloride ion concentration, so even after you make your friction stir welds, if you want to do something like that, you can really do it real easy, right? You can make different solutions and put your things and monitor them carefully. But talk to a chemist when you prepare your solution. Preparing something right. And here, good observation. Yes, sir. Very good. Yes. Yeah. So the reduction is almost from 450 to, yeah. The percentage reduction is way high in the 7,000. Yeah. Which is, but that's, yeah. Very nice. Thank you for pointing that out. And here are the failure times. So basically, this is strain rate at 10 to the minus 7. 10 to the minus 7. It takes a long time to do a test in 10 to the minus 7. Many of the tensile tests that we do in the laboratory are 10 to the minus 3 per second. That's the strain rate that we all use when we write 10 to the minus, yeah, 10 to the minus 3. That's what we use normally when we do a tensile test. But if you want to see the effect of environment, like chloride ion concentration or relative humidity, for example, those two come to my mind when it comes to aluminum. And if it's titanium, maybe it's alcohol, methyl alcohol or something like that, where it attacks. But you have to run it at a slow strain rate so that there is time for the ions to react, right? So goes up and then comes out. So this is because of they exhibit a maximum with respect to chloride concentration. Is a transition from pitting corrosion to passive corrosion as the chloride ion concentration changes. No, I will change this sentence. Sorry, I don't think this is right. So here there is corrosion going on, pitting corrosion. But then at this point, you have a passivating layer. Right? So if I have a piece of aluminum and a passivating layer formed on it, aluminum oxide is a passivating layer. Titanium oxide is a passivating layer. That means it's a very hard layer which the chloride ion cannot break it that easily. But of course, it will break it eventually. But that's a barrier. It forms, and then it goes away, right? So up until here is going up. But then here, I think there is a passivating layer that forms. So it's so there is a competition between passivating layer and dissolution of the passivating layer. It's kind of down. But who wins in the end? The dissolution. Okay? Because once the dissolution of the passivating layer took place, then it's going to start losing its, it's going to start corroding more. So the trends are same, both for the 5000 and the 7000 series. Huh? Oh, yeah. What you're talking, you mean like this? Huh? Yeah, it could, okay, yes, what you're saying. Yeah, it could have been a straight line, but this shows there is definitely an effect of the chloride ion concentration. Yeah, at a constant strain rate. At a constant strain, right? And now you can do the same experiments, varying strain rate. So constant sodium chloride solution, one sodium chloride concentration, but change the strain rate and do the experiments all the way from 10 to the minus. Okay. So high this way. So yeah, high this way. That's strength. pH? Yeah. Is it an indication of chloride ion concentration? I think so. I think so. I have thought about that many times. I think so. Because if you have a pH of 3, it's very acidic, right? And if you have a pH of 11, it's very alkaline. But you may have to add some other buffer to make it more alkaline. You cannot just keep reducing chloride and think you will get to 11. You're not going to get to, yeah. I'll give you the paper. Take a look at it. ASTM standard will be there. ASTM standard will tell you exactly if you want to run variation of pH or variation of hydrogen chloride concentration or variation of pH. Yeah? Yeah. And I can't be good at everything. There's some things, I'm not sure. I'll ask somebody who is, no big deal. Just, that's what they do every day. Yes, absolutely. Yes, very important, very important. Yes, exactly. There you can see that the strain to fracture is decreasing as the strain rate is decreasing. Right? You're giving more and more time for the chloride ion concentrations to react with the metal. Right? So good work, good, nice data. Right. This one? First one, okay. Oh, yeah. So NaCl solution. Yeah. Right. Yes. So this is lower strain rate, right? This is lower strain rate here. Air and sodium chloride. Oh, but this one, right? UTS. Are you comparing this or this? This one, right? This one. So there is your air, no effect. Yeah. And there is your sodium chloride. Sodium chloride, right? Right. Air is not, there is no effect. Yeah. So are you saying maybe no, I know. No, he knows that. He knows that. No, I see what you're saying. What he's saying is at high strain rates, there's no effect. Yeah, that's what he's saying. And there's no time for the, yeah, that's what he's saying, right? That makes sense. Which one? They do get affected actually, but oh, I see, compared to the other materials. Oh, yeah, they don't get affected that much. Yes, I see what you mean. Sorry it took me so long to understand. Yeah, I mean, yeah, okay. Right. But this goes to show that if you have a component that's slowly, creeping or slowly, even at very minute strain rates like 10 to the -8, you're going to have serious effects. In steels, okay. Yes, it is worrisome, yes. That's why we're very worried about stress corrosion cracking and 7000, 7075 always, because many of the components out there are 7075 T6. Many of them, almost all of them. Not peakage, yeah. Yes. Yeah, exactly, yes. Absolutely. Yeah, absolutely. Yeah, okay. There are some other things that popped in my head now. Okay. See. Huh? Coatings? Yeah, they will. Yeah, always aluminum components you will put a coating. Always. We clean it up with allodyne, which is a chromium containing primer. Okay. And then the top coat would be, magnesium rich. But I'm not able to tell you exactly because there are green coatings and non-green coatings. Who was talking about green coatings yesterday? Yeah, green coatings. Yeah. So green and non-green coatings. Yeah. So, I mean, non-green coatings are all chromium containing, basically, because they're the best. But chromium is being banned, so you're trying to look for replacements of chromium. And so far, the research shows that we do not have anything that works as good as chromium, unfortunately. It's banned, yeah, it's banned, but military will use it with every now and then. They get a waiver, They'll cause cancer because chromium is always plated. If you're putting a chromium coating, it's always an electrolytic bath. So the vapors, the guys who are working, it can cause cancer. But once it goes on the thing, it's okay. But during the plating process, yes, it's the breathing effects, cancer causing substance. Okay, so basically, let's see one more. Maybe there is some, okay, yeah. Maybe you may be interested in the fracture surface. So the bottom one, I didn't write it down, but this is 5083. So this is the surface, this is the fracture surface, okay? So there is the sample, tensile sample, there is the fracture. You make a section like this, perpendicular to the fracture, and you take these pictures, okay? So there is my tensile sample, for instance. There is my fracture, okay? So I take this fracture surface. So I take this fracture surface, and I make a cut like this, and look at this plane. So that's so the plane is perpendicular to the fracture surface. Yeah? Okay. So that way you can see what is going on below the fracture surface. Exactly. Right? Huh? Yeah. Yeah. Right. So big intergranular cracks. At first I thought it was exfoliation cracking. You know, exfoliation is also one of the corrosion forms. But I thought that is exfoliation, the way the grain lifted up. But Rick says that it is exfoliation, so it must be right, because he's the expert. Okay, but I think it's whatever it is, but you can see how long it has. This is 100 microns, 0.1 millimeter. You can see that's a pretty long crack right underneath the fracture surface. And you can also see there is a crack right there beneath the fracture surface. Okay? This is for 7075, this one. So actually, let me write that down, because once we put it in the book, you will not know which one is which. So, right? Insert. $7075. Change the color on that. Yeah, I can put white, but will it be okay in the print? Huh? Will it be okay in the print? Amit, if you put white there in 7075, will it be okay in the print? It should be, right? It should be okay. So, because 83. Let me put it here, black against white. Okay, so this. Okay, so basically, yeah, that's what we have there. Okay, you can read this, no big deal. Okay, so we are done basically with that part. I'm just going to show you from yesterday. Some of you were, so this is the slip bands. So that's how they look like in the TEM, slip occurring in the planar slip bands. Okay, you can, in the transmission electron microscope. And here is a schematic. That's the best I could do at that time. Slip band spacing and width of the slip band. Ready, Garu? Ready. So here is the slip bands, dislocations in slip bands. For the fracture toughness model, okay? Just a schematic. Wide slip bands and low slip band width and spacing for underaged. For peak aged, larger slip band spacing and narrower slip band width. Okay, Huh? Oh, you did, we did this? Oh, yeah, I wrote it yesterday. Yeah, yeah. Yeah, yeah. Yeah, yeah. So here is the model. I just kind of put more steps in here. So this is the crack. Don't pick my mistakes here. So here is the crack opening displacement. Okay. In front of the crack opening displacement, number of dislocations times Berger's vector. Alpha is the inclination of the slip band. On that slip band, you have n dislocations times Berger's vector for each. Okay. This twice comes because of some. You can put 3. No, you can 2. Okay, that's fine. And then these slip bands, we divided them up into 2 parts. Okay. Some of them are homogeneous, some are heterogeneous. Because not all dislocations are in the bands. There are other dislocations too. You have to consider both of them. Okay? You see what I wrote there, the paragraph, right? The dislocations in the front of the crack tip may be homogeneously distributed or heterogeneously distributed in intent slip bands, right? We'll be done in 5 minutes.
Yeah, sure.
So that we'll be done with this few graphs today. Okay, so that will be the crack tip of opening displacement. And then the density of the dislocations, yeah, number of dislocations, right, divided by length of the slip band, and W is the width of the slip band. Okay? I'm glad you guys are all agreeing. Okay. Several people have agreed with it. So, yeah. So density of these dislocations, all this stuff, okay. Anyways, we come up with this, then we go back to our crack tip opening displacement, which is K squared divided by Young's modulus, sometimes yield stress, on, and we come to this K1C is equal to, in terms of the dislocation, slip bands, widths, and all that stuff. So I put everything down here, okay? Also, I put down here the plastic zone width, parameters, plastic zone width calculation, D. And the next one we have picture taken of the plastic zone. So it's not a round, nice round one in the book, like in the books. Well, no, book also puts this wing-shaped plastic zone. Especially in these kind of materials, you can see, you got both this wing and also that wing. So the plastic zone is not necessarily a round, nice plastic zone. It's, the plasticity is spreading along this plane, bunch of planes along this direction, a bunch of planes along this direction. Yeah. And this is the crack growth direction. Okay? Huh? Is it okay, Shinde? Okay. Okay, and then here is the fracture toughness experimental, and here is the predicted line. Okay? So they have modified this since then. They have not changed the fundamental premise. They have done more elaborate calculations. I don't know how they look like now. Here is the one I wanted to show you. Let me put the lights off just for a second. This one. So this is a typical slip band cracking. It looks like intergranular, but it's not. See how these are. And look at this one. It's called rough fracture surface. So these tests were done in air. These were done in air, and these were done in vacuum. Done in vacuum where there is no air. Remember yesterday I was talking about if there is relative humidity, the dislocations will carry the moisture into the material. This is, of course, there's no moisture here, but there's regular air. I don't know what the humidity was, maybe 25%, 30%. But you can see the same conditions, everything same, except this is air, this is vacuum. These surfaces are perfectly still, you know, right? Yeah, slip band cracking, which looks like cleavage actually, yeah, but it's a slip band cracking. So that's even nickel-based superalloys. You'll find a lot of slip band cracking, which looks like intergranular or transgranular cleavage type of, but there are no river lines. That's how you distinguish. Okay, I just wanted to put, I'm going to put this in the binder. Huh? Okay, I think that's, yeah, that's all what. So those are the loose ends from yesterday. We'll have cookies and coffee now. Save, don't save, save. I want to put this on the server. Oh. 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 Sorry, it's taking me a little bit of time.
You want this in a full screen?
Yeah, I'm trying to put it on the desktop. Oh, okay, that's fine too. Can I use this like that? Yeah. It's hard today. Okay, so we're going to wrap up the stress corrosion cracking in the next 45 minutes to an hour. Yeah? What do you think? That way, we'll only have Monday morning, we have somebody coming, American Society for Metals. Right? So they want me to give a talk on nickel-based superalloys for 2 hours. Why? Huh? So you're the guy who's asking? No. Huh? No, I don't know. I'm okay. No, that's good. That's good. Yeah. So yeah, be here on B Square on Monday morning. Okay? No, yeah, there are some ASM people. I think they made a request to Amit. So we'll discuss about 2 hours, Monday, nickel-based superalloys. I think I'm going to have the same format. Well, not same I don't have a format right now, but we'll have processing, microstructure, and fatigue and all that. But it'll be mostly towards. Yeah. So we'll have. I will speak from an application point of view. Like blades, superalloys are all castings. Not all, most of them are castings. And then wrought materials are not castings. They're for turbine discs and other things. Turbine discs. That'll be good. I'll take those two examples and build a story around it. And then equiaxed, directionally solidified single crystals, and then different solutionizing elements. Again, what are precipitates, what are grain boundary particles, and those. A little bit of repair. Repair, yeah, that's actually a very important thing for nickel-based superalloys, but because they're so expensive, the parts are so expensive, you can't just throw them out, which we do. So the question becomes as, Kumar is asking, I don't know, Dr. Kumar is asking, right? What do you say first name? Jalag, right? Yeah. Huh? Jalaj, yeah. So as he's saying, those are important things, those are important things. So this is the last bit of corrosion. I mean, I have a lot more corrosion to talk about. Oh, coatings maybe we'll talk about at some point, a little bit of coatings, yeah. we'll talk about a little bit of coatings. I think we can talk about at least what's going on in the world, with respect to coatings development to stop corrosion, or to protect the structures from corroding, right? Because we cannot stop corrosion. You can try all you want to. It's not going to happen. It's tough. But this is the last, maybe we already did this, I don't know. Maybe some of this is repetition, maybe, but it's okay. It's okay to revise things. So like I said, stress corrosion cracks are always branched. That's how you can tell a difference between a stress corrosion crack and other cracks. So again, this is the fracture surface, okay? And we made a section like this, and we're looking at, like this, right? So, and also we set these kind of boundaries, the straight boundaries are no good when it comes to stress corrosion cracking. Huh? Yeah. Oh yeah, okay. Yeah. Yeah, that's fine. Desktop is fine. Okay, that's PDF, but that's okay. Okay. Yeah, that's fine. Yeah, that's good. Yeah, no problem. Actually, there is a little square. It's not visible. It's probably at this corner here. Yeah, just it'll go away. It'll go away. I mean, it'll go away. Yeah, yeah, yeah. I'll go up. I'll go up again one more time. Yeah, thanks. Thank you. I'll go up again a little bit. Yeah, that's good. Better, right? Very good. Okay, so whenever you are working with materials which have got these grain boundaries like this, you have to worry about stress axis along this direction. You really have to worry about it because these grain boundaries are perpendicular to your stress. Once the crack starts, there's no way to branch out. There's no way to branch out. It's going to go right along these lines. Okay? And that happens in very alloys that are, commercial type of alloys. Huh? Yeah. Right. Yeah, so a lot of times what we do is, if this is your fracture surface, we put something on top of it to protect the surface from deforming when you polish it, right? What do you put? Nickel plating. So you have to put a nickel plating here to polish and then polish it, so that these avoid, yeah, to avoid the rounding of the surfaces, and also, yeah. You were going to say something, or okay? So yeah, nickel plating. Can you nickel plate any material? Can you nickel plate any material? Yes, any? Yeah. Yeah. What is the? Yes, madam. Okay, she's authority. Okay, we've done everything in DMRL. I agree. You guys are good. So here is so this is an interesting fracture surface of a overaged aluminum alloy. So remember what we said in the overage condition, we have precipitates on the grain boundaries. In a precipitation hardened alloy, we have precipitates on the grain boundaries. So when it fractures, you see these voids on the grain boundary. This is a grain boundary actually. You can only tell if you're doing many of these. So don't worry. Well, I cannot tell if it's a grain intergranular fracture or not. But if you do many of these in that condition, eventually you'll find out, oh, this is a grain boundary, and these are coming from the grain boundary particles. Okay? So this is a intergranular microvoid coalescence, IGMVC. So it gets a little bit complicated, but it's not. It's just the word is complicated. It's too long. I cannot say it in one. So intergranular microvoid coalescence. So it is an intergranular fracture, but it's got microvoids on top of the grain boundary. So intergranular microvoid coalescence, this happens in overaged I should write that actually, but this is a PDF file, right? This is a PDF file. I cannot write in, I don't have a PDF writer. Okay. There is a comment thing here, comment. Huh? Tools. Add sticky note, that's good. Okay. Intergranular void observed in fracture of overaged granular. Okay. So intergranular microvoid coalescence. It's all one word, so I'm going to put hyphen. Huh? It's an intergranular fracture. Even though you see voids, okay. The voids are due to, excuse me, typo. Due to the precipitates. I won't write sitting if I'm writing a paper. I'll just write residing or, I'm just writing this, sitting on the grain boundaries. Overage overaged. Okay, overage condition. So I'm just going to leave it there, and then later on maybe we can, maybe we'll take care of it. But we have at least a comment there, okay? So one important aspect, 2 or 3 important aspects. So we can have, in the stress corrosion cracking, SCC, we can have transgranular stress corrosion cracking, which is going along the grain, inside the grain boundaries, stress axis is like this, or we can have a intergranular fracture. Okay? We can have both the stress corrosion cracks. So this is again, you're looking at so there is the fracture surface. It doesn't have to be fracture surface. It's any surface that is exposed to sodium chloride solution or something, and you cut perpendicular to that surface, and you can measure the pit depths. So this is pitting. You can measure the pits, and there is a crack coming out from one of the pits. It's interesting that this pit, even though it's larger than this, doesn't have a crack. It's kind of funny. So a lot of times what you can do, you can take this as a tensile sample and do your high cycle fatigue life to see what is the fatigue life in the presence of pits. Okay? Because the corrosion pits affect the high cycle fatigue because of those kind of cracks coming out from the pits. Oh. What did we do last time? 1 second. Hi, Aaron. We already did that. What did you say?
Can measure crack size.
Yeah, you can.
Critical can be found.
Yeah.
Crack. Able to
Right. Yeah. No, I'm just saying you can. I'm just giving you an option. We don't have to. But if you're interested in seeing what is the effect of pits on the high cycle fatigue life, you can do something like this. You can take a panel, put it in the salt fog chamber, right? Or Chennai West Coast, or wherever you want to, or East Coast of Chennai, right? East Coast, yeah. Or Calcutta, or anywhere. And you can take that panel, you can look at the pits, you can make a sample out of it, run in high cycle fatigue, and then you can look at those also. Output of this testing is,
yes, you can measure initial crack size. Yeah. And the final crack size you can calculate. You can
without doing any test? No. You cannot get anything without doing the test.
yeah,
Right. But what I'm saying is, for instance, that is the largest pit in this, but I don't see any fatigue crack there. I do see the fatigue crack here.
you can measure the
Huh? Yeah.
initiation crack. Yeah. Critical can be found out.
Sure, you can. Yeah.
Now you know the formula for enough number of cycles.
Absolutely.
That K vary only we have to click.
Yeah.
That K. In the MRO, you don't
Yeah.
have this concept. Number of cycles.
Sure, of course, sure. Yes.
So doing testing.
Sure, you don't have to do testing then, yeah. Of course, you'll have always the doubt, what will happen if I do the test? No, you're right. I mean, you can do a statistical distribution and do that, yes, absolutely. And that's what you may end up doing eventually. But as a student, for instance, some of these people who are doing master's thesis, PhD thesis, sure, they can do modeling and simulation, but they also may want to look at experimental work, Verification.
Experiment also.
Well, you're looking at the pit sizes,
I said
SN fatigue. You look at number of cycles to failure. Yeah. I showed you that yesterday, right? Yeah. Yeah. I showed you that yesterday. I can show it again. I'll show it again. Yeah, I know there are so many things we're talking about. I was going to write here something. I'm just going to write it down anyways. Something I had in my mind. Fatigue crack emanating from a pit, right? So, which will lead to failure, if the above is under cyclic fatigue load, right? So this is something, hydrogen embrittlement. Where is our hydrogen embrittlement? Hydrogen embrittlement, right? So here we are, like a crack, there's a crack. It's just a schematic. I'm just showing you a schematic. There is a notch or a crack, and let's imagine there is some hydrogen, or even coming from outside too, or internal, doesn't matter. See, right in front of the crack tip, all this hydrogen will collect, because of the elastic field. There's always a question that comes up on the exam. Hydrogen is an interstitial atom. Where is it going to go and reside on a dislocation? Because if you put a dislocation, right? If you put a dislocation, so if I put a dislocation, there is my dislocation plane, right? So there is my dislocation. This is my dislocation line, right? And this is tension side. This is compression side. I hope I'm right. Check it out. So if I have the hydrogen, if I have a hydrogen, will it go and sit? Okay, these are all the lattice points, atoms. Atoms, right? So where will this hydrogen go and reside? Will it go on the tension side and sit somewhere, or will it go on the compression side and go sit side, or the compression? A favorite question always. I won't give the answer right now. I'll let you think about it. Then we'll have an answer afterwards. Okay? I'll let you think. I'm not expecting to think about right now and tell me right now. No. Okay. I'm just telling you that's a very popular question that people ask. Okay. So here we are. There's the maximum stress in front of the crack tip. Okay? Maximum stress. So whether it is internal hydrogen, yesterday we were talking Bhanumati, remember? So if I have a sample here, this is my sample, okay? And if my sample has 100 parts per million of hydrogen, okay, my sample has macroscopically has 100 parts per million, but right in front of the crack tip, it will be much, much more than 100 because the hydrogen is all coming. It will all come from everywhere, and it will sit at the highest stress level. So even though it's 100, here it may be 300, 500, and I can have hydrogen embrittlement. You see the point? Yeah. But if you don't have stress, it will all be 100. But if you have stress, it will all collect there and become much more. And there is an equation for that, actually. Equation, yeah, I may have to. Okay, there's so much material out there, right? And same thing, even if it's coming from the outside hydrogen, from the outside, you know, the crack tip will attract the hydrogen from the outside. It will all collect there. Again, there is your concentration. So that's where, because now these bonds here, all this lattice structure here is going to experience this stress field from this crack tip, and this hydrogen is sitting somewhere, and it will reduce the energy. It can reduce the cohesive energy. This bond may break, this may break, that may break, you know. So you can have a hydrogen embrittlement. See? Right? Makes sense? So I thought I'll put this up there. We just saw this, something like this, right? So this is a very popular test we always do. Instead of going and machining our fracture mechanics samples right away, which are very expensive. So for instance, Shinde, in your case, you're doing the epoxy patch on 6061 aluminum, right? So you can make samples like this, or you can take that 6061 with epoxy patch, put it in sodium chloride solution. Not solution directly, but expose it to sodium chloride and see how well the epoxy patch functions in sodium chloride environment. Because that's very important for repair. Very important. You know, maybe you patched up the patch very good, but will it survive the corrosion? Will it survive fatigue? Those are the very important questions. So this is a very important thing. For somebody like your work, I think it's very critical, actually. Will the epoxy patch on aluminum, will it survive? That patch will stay there in sodium chloride environment, right? If the aircraft is sitting, which is repaired, and it's sitting in, you know, in a very humid atmosphere, will it be able to sustain the high level of, you know, salt in the air? And if it survives, how long will it survive, right? So we can do a test in the laboratory, right? You think it's important, yeah. So here is a common test that we all do for stress corrosion cracking. Simple tensile tests, elongation stress at different strain rates. Just like we talked about before the break, right? Before the break, we did, you know, fracture strain as a function of strain rate, right? And, Jalaj Kumar had a question, you know, he was telling us, had a comment, rather, another question as to how it's getting affected. So here also you can see, I'm not going to go through these 100 lines here, you know, but it's going to reduce as a function of time. So this is much not faster, but cheaper than, because if you're doing it at a very slow strain rate, it's going to take some time. Okay? But these tests were done in air at slow strain rates. Okay, so I also see one more thing here. You can also do these tests by applying a potential to the specimen. Okay? So this guy has used silver chloride as a reference electrode. You can have a hydrogen electrode, or you can have a silver chloride as a standard electrode, and you can put a potential. So I have my specimen, and I attach with a crocodile clip. Is that what you call? Alligator clip, not a crocodile. A crocodile clip. We say alligator clip. Same thing. alligator clip with a standard reference electrode, alligator clip with a potential, some potential. So you have applied a potential to this specimen. You can put cathodic potential or you can put anodic potential and see how these things get affected. You can do all kinds of tricks. But there is the reference, Torkelly. But there are many other nice references. Okay? There are about 10, 15 diagrams which all look like they're all similar. Okay? But the main thing is this, that so this is the test that you're doing. We didn't use any paper today. No, that's yeah, we don't have to. But I was just saying we didn't use any today. It's okay. It's okay. It's okay. I think we're just repeating some of the same thing. So here is my. So here I'm going to do something like this. Here is my compact tension. Let's do a thought experiment. Here is the crack. Okay, we'll put a small crack in it. Can we borrow your epoxy patch? We'll borrow your epoxy patch. That epoxy patch repair there. Okay. We can put it on either both sides or one side. We'll use Dr. Shinde's epoxy patch, and then we can do stress corrosion cracking test now. Okay. Maybe we should put the patch on both sides. Or you can take a center crack panel. Okay. So anything. I'm just putting something here. Okay. Just to illustrate that you don't even have to have the epoxy patch. You can just have a regular crack also, and do that kind of test. Oh yeah, unload this. Load this. Put a load on it. Dead load. Put a dead load on it and see how the crack growth, how the crack will progress, and we plot test intensity on the x-axis, dAdt on the y-axis, dAdt on the y-axis. So normally the books will tell you that you're supposed to get 3 regions. Region 1, stage 1, region 1, stage 2, plateau region. The crack is moving still, but dAdt is constant. Okay? So if you plotted A versus time, the crack is still moving, but the slope is a constant growth rate. This is growth rate, constant. And this is the stage 3, fast crack growth rate. Okay? So this is ideally, this is what is supposed to happen. There is a guy called as Marcus Pidal who did a lot of work from Switzerland back in the 73 or something. He did, can't imagine, he just did for 3-4 years the same work. So here he compares 0% copper, 1% copper. Effect of copper on the stress corrosion cracking is a big difference. So the author's name is what was the tool that you used? There. Okay. So Marcus Pidal, S-P-I-E. Classic work on 7,000 and 2,000 aluminum. Okay, this is where everything comes from. Forget about this. So here you see how beautiful data he has produced. Unbelievable. With scatter also he plotted very nicely. 0% copper, 1% copper, 1.6% copper, 2.1% copper. Fantastic data. How the plateau velocities go down as an increase of copper. And then you can think of why is it doing that. But first you have to get this beautiful systematic result. Very nice. But no effect on the, not a whole lot of effect on the K1SCC threshold. Right? This is the K1SCC. It's like a threshold. Right? Stress corrosion cracking threshold. That means below this stress intensity, there is no crack growth. Okay? But a lot of, what is it, 2 orders of, maybe 1.5 orders of magnitude change in the velocity, crack velocity. Yeah, he has. Yeah. Yeah. Oh, the previous one. Yeah. Yeah. So he has kept the temper constant. Yeah. Oh, I see what you're saying. Okay. Yeah, sure. Yeah. Oh, yeah. So, yeah, you're right. Yeah. So the dark lines are T6 and the dotted lines are T73, T751, T7351 or something. So T6 is your peak aged and T7 is your overaged. So he has taken that sample, put it in the furnace and aged it for a little bit longer time, and he got the overage temper. Okay. Yeah? Beautiful work. Yeah, oh, yeah, it's known all over the world. This guy did a very nice piece of work. Got a lot of patience to do this work in a very systematic way. You know, a lot of times we're afraid of spending so much time on a project. You know, we have other things to do. Especially the guys, where are the Bharat Forge guys, you know. They have other things. Meetings. Right? How many meetings do you have every day? 2? 2 to 3 every day. Yeah. You're in the middle of your work and somebody has a meeting to go to. Okay. But that's the way it is, life, right? So here's a beautiful graph. Stress corrosion velocity, that means plateau velocity versus relative humidity. Geez, look at that graph. Beautiful straight line. Oh, look at this. As the relative humidity increases, velocity increases. That's okay. Effect of temperature. Yeah. That's why prediction of corrosion is very difficult. Yeah. It's a very controlled laboratory experiment. Yeah. And also temperature. So now you can see what professor is saying. This is only a relative humidity. Now on top of that, you also have a temperature effect. And then you can have a sodium chloride effect. You combine all these three and try to predict the corrosion, it's difficult. Very difficult. Because this temperature is changing all night, all day, right? All day and night. This is a constant temperature nicely done in the laboratory. You know, 23, 50, 75, 90, 100. Wow, what a beautiful, right? Nice changes. If this is your thesis, perfect. No problem. But again, no effect on thresholds. Just plateau velocity. And look at the change. Oops, sorry. Look at the change. Goodness. This is 10 to the minus 3. 10 to the minus 3, minus 2, minus 1, 0. 4 orders of magnitude change. 4 orders of magnitude change going from 23 to 110. So maybe this is nighttime, winter, summertime, daytime. 4 orders of magnitude. That's too much. Aluminum alloys are very susceptible to temperature. If they're under stress. Actually, I would have liked to see what happens when you go down to -40. Because the airplanes are flying up in the altitude, which is -40, right? Most of the time. Whether you're on top of India or on top of America doesn't matter. It's always -40, about -40, -50. Everywhere in the world, almost. Huh? Well, at least we know that there are issues like that, so we can be prepared. You can't change much. You cannot do anything. But only thing is you can design your aircraft keeping this in mind. That's all you can do. But this is the peak age, T651. T651. So if you have a crack, that has got a stress intensity that K is equal to sigma times square root of pi A, if you have a crack that's got stress intensity of 5, you know what the variation would be, right? So people are still trying to model, stress corrosion crack. Corrosion. There's a lot of work going on. Everybody's trying to do their best. How can we predict corrosion? Because of the number of variables. Temperature variable, salt water variable, humidity variability. So you cannot just do linear regression and say, okay, some coefficient times temperature, some coefficient times relative humidity, some coefficient times precipitates. I don't know if that's the answer. But you see my problem, right? Oh, we were just talking about minus temperature. There is a minus temperature here. Oh, by the way, this is the worst alloy you can have, 7079. If you want to see bad things happen in your research, you want to see big effects, pick this alloy. This is a terrible alloy, 7079. But it's a good alloy for research. You will get results fast. You'll get fast results. It's going to break very fast. So you don't have to wait too long. Your thesis will be done faster. But look at the effects, nice effects. -11, -3, -21, 50, beautiful. But look at how fast the crack is growing. 10 to the -4 meters per second, multiply that by 10 to the 3, it's 0.1 millimeter per second. Right there in the top. Right there. Right there in the top. That's 10 to the -4 almost, right? Times 10 to the 3, that's meters per second. That will give you millimeters per second. That's almost 0.1 millimeters per second. It's running. The crack is running even at this low stress intensity of 5 at that temperature in this material. They don't use this anymore in the aircraft, but they used to use this at one time. K1, this is K1 SCC. I mean, when you say K1 SCC, that's a threshold, right? So these are all K1 SCC, like at 105 degrees Celsius, this is the K1 SCC, this value. But this is stress intensity K, but it is in at 105 degrees. But it's a stress, it's not fatigue, it's just a stress intensity. If it's fatigue, it will be stress intensity range. That's what you have to look for the word. Range would mean fatigue. If there's no range, it is single. Yeah, but that means, what is it, 10 to the minus 8. Maybe he got too tired of experimenting this anymore. So he said, okay, let's stop it. I mean, it's probably going to go straight like that, most likely. So basically what you do in that case, you're defining your threshold at 10 to the minus 8. Or even 10 to the minus 7, you just draw a line, horizontal line. You say, this is where I'm defining my threshold. As long as you say that, you're okay. Threshold for 10 to the minus 7 meters per second. But I know what you're saying. You don't have to go to 10 to the minus 10 every time. I mean, if somebody who's giving a talk after you, and he shows 10 to the minus 10, she'll say, well, you did only till 10 to the minus 8. Look at my data. I went on to the minus 10. So that's all. Did we see this? Yeah, we saw this. Well, we saw this, but it's on a different material. 10 to the minus 3. Okay, let's see. Yeah, absolutely. Okay, anyways, this is thick plate, 2.5 centimeters thick plate, 1 inch thick plate. But look at here. This is iodide, I think. Yeah, iodide and bromide. I don't know. Anybody interested in the iodides and bromides and chlorides? Okay, so you're interested? This is the short transverse. Can't read it very well. I don't think you can read it either. Need to retype these things in. We need to retype these things. So this is short transverse SCC. Okay. So this is the thickness direction of a plate. Okay, that's where the weak points are. The weak link in this material is in aluminum alloys. A lot of times when it's a thick plate, if it's a sheet, there is no problem. But if it's a plate of aluminum, you have to make sure that you understand this very well. Okay, so this is through the thickness. Oh, okay, we'll just use it here. So the grain boundaries are like this, basically. Okay, you're loading it like this along this short transfer. Let me tell you something about the designation. In these kind of specimens, if I don't put a designation, you will never know where I took the specimen on a plate. So what I'm supposed to do, if I put S, that means my stress axis, the crack is growing along the second one, crack growing along L direction. Okay? The stress axis or the loading axis along the short transverse direction, S direction. It's very, very important to mention this, especially if you're working with a plate product. A plate product, so if it is only this thin, it's a sheet product. But if it's this thick, it's a plate product. If it's a plate product, it must be mentioned, very important. Because this is so So that means I have taken a specimen like this. That is that specimen. Okay? So if I take a specimen like this, for instance, let me put just arbitrarily something. If I take a specimen like, well, let me make it a little easier for us. Oh, I think, yeah. So let us put the stress axis, that way is fine. Track is this way. So in this case, so this is this S direction. Let us say this is the transverse direction. And let us say this is the L direction. Okay. So this is my S direction. This is my T direction. This is the L direction. And this is the S direction. So this is a stress axis is T. And the crack is along the L direction. Okay. So this is my TL specimen. Okay. And if I take a specimen here, S direction is my stress axis, crack is transverse direction. Right? Although my drawing is not the best, but it is okay, right?
Because L in
So the first symbol is the stress axis. The second symbol is the direction of the crack. First symbol, I didn't write that down. Oh, okay. I didn't write it down. Yeah, I didn't write it down. So first symbol is loading axis. Direction, loading axis, direction. Second symbol crack growth direction. So if I take a S cell specimen, the stress axis is along the S direction. Crack growth is along the L direction. So this should be the case. S direction is my loading. L direction is my crack growth. If I want an LS, no, well, that will be tough. No, it won't be tough, but LT, for instance. If I say LT, that means my stress axis should be along the L axis, which is, this is my L axis, right? L, okay? That should be my, the loading should be along this direction. Okay? And the crack should be along the T direction. T direction. Okay? So loading along the L direction. Of course, I'm not L direction. My T direction is this. So my first symbol is the loading axis. And my second symbol is the direction in which the crack is growing. This is what we follow for the fractional mechanics samples. If you don't give this, then we're in trouble. Huh? L is rolling direction. Yes. S is the short transverse. Short transverse. T is the long transverse. So this is the designation that we follow. It's not the best drawing in the world, but I'm hoping you get that picture. What is the difference?
No. What is recommended by standard or to find out?
Yeah.
Based on that, you
Exactly. Yeah. 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 So if you're very, in your case, so maybe you want to check LT sample in your case, the loading direction along the plane of the roll, along the direction of rolling, and long transverse is your crack direction, you make it like that. But if it's a thick plate, always in the industry, they're always worried about what is this toughness? What is the toughness when I'm loading like this? Because that's the Achilles heel for a plate. It's the weakest. This is the weakest thing for the plate. If this is 4, K1CF 4, this is K1CF 30, I would be scared about this 4 in my design. So I need to bring it up at least 12, 4, 15, something. If it's 4, I will be worried. So if I come to you and say, Shinde, I got the greatest aluminum plate in the world, say, what is it? Short transverse toughness. Tell me what it is. And if I tell you 4, say, go back home and do some more homework. Then come back. Yeah. Yes. Yes, they should. They should. For thick plates, they should. And even for thin sheets, yeah. Yeah. Yeah, yeah. So you want to know that spectrum. Yeah, you want to know the lower band and the upper band. If you can live with the lower band, that's fine, no problem. You can live with it. If you say, I'm never going to encounter the short transverse direction in my application, you don't worry about it. So if I'm making an antenna, for instance, out of a plate, and if my antenna direction, is not the short transverse direction, it will never be actually, because so long, I cannot have such a thick plate anyways. I don't have to worry about it. So if I take an antenna, for instance, out of an aluminum plate, which is, either like this, if it's like this, I'm not so worried about it. But actually, even then, better than this, well, or that way. Okay? So, yeah, of course. That's why we're saying the second symbol is the direction of crack.
Actual direction.
Right. Yeah. You have to tell the direction of the crack. Okay. I just want to tell you this because it's important, okay? Also, yeah, you have to show that also. You mean designate the axis? Yeah, you can do that, yes. With respect to the plate, actually. So if my plate, if this is my plate, this is my plate, You can see it from here. This is my plate. This is short transfers. Forget about the axis. This is my short transfers through the thickness. This is my short transfers through the thickness, right? And this is my rolling direction, right? So if I machine a sample, the loading axis is like this, and my crack, the crack is this, right? You know, that's the way you'll machine, most likely. So the direction is S, and the crack direction is T, long transfers. And if I do this, my direction is short transfers, rolling direction, the crack growth, right? And if I do it on this plane, let us say I take a specimen this way, and my axis, loading axis like this, it's parallel to this, trans T, L. Okay, this is my long transfers. This is short transfers. This is my rolling plane. Rolling plane, loading direction. You go through it a few times on your paper and it will be. Is that what your question is or no? They're perpendicular to each other. Even if they're not perpendicular to each other, they still would not matter so much because you still have you'll retain the same thing. So even if you take a section out of this, so this is my plate, if I cut out a section like this, okay? Yeah, it's exactly not parallel to L anymore. You're right, absolutely correct. But through the thickness is still there. This is not going to change. This is probably changed. This has changed because of this. But this thickness is still the same. Through the thickness is still the same, except now they're a little bit at an angle. But they still have the same lamellar, see this plywood, how it is? How these lines are? So even if I make a cut here, you still will have those lines there. Right? Do you agree? We have a saw, let's cut it and see. Yeah. Yeah. So yeah, that is a good question here. I mean, very good question, yeah. He's supposed to tell you. Absolutely. He has to put it with a scriber. You know the scriber, right? He should put it with the scriber. You know, usually they'll put a serial number, right? They'll usually put a serial number. Yeah, they're the Bharat Forge. They're going to tell you. Exactly. Yeah. Yep. So the middlemen are like that, huh? Huh? And cut it without keeping track. Ah, yeah. Yeah, but if you don't know that, you'll be in trouble, yeah. So even when you're doing tensile samples, even if you do the tensile samples, it is important to know what is the longitudinal direction, what is the transverse direction. It may not make a difference, I don't know, but it depends on the product. But what I'm saying is, it's still important to know, okay? If you are building something, so he gives you a subcontract to you. It's waste of his time to do that. He gives you a subcontract, it's cheaper for him. But you still have to tell him which is L and which is T. If you don't tell him, he says, well, you know, I don't want to hire you next time. As simple as that. His boss is going to ask him, which is L and which is T. Yeah, unpolish it. Huh? Grain flow? Yeah, exactly. Yeah, that's true. That's true, grain flow. No. Metallographic analysis. Yeah. Yeah, go ahead. Macro etching, yeah. You don't have to do micro, yeah. Well, that will be a little bit longer route, but that's, yeah, the simplest route is macro etching. Yeah. Yeah. Yeah, but you don't have to do that. That guy is supposed to tell you that. I agree. No, I agree. Yeah. These are all the problems that we face in real life. It's totally different, yeah. I know how it is. At the end of the day, I say, you know what? I got a headache. Let me go home. We'll talk tomorrow. I'm getting a headache, I'll go home. No, I mean, that's what will happen. You're right. So anyways, these are all very good data points. I mean, you know, just something to keep in mind. Okay. Yeah. We will go through it again next week. Okay. It's time, right? 1 o'clock. Okay. Yes. Yes. Oh. Abba. రేపా